consider the rotation of a rigid body about a fixed point. So we have a rigid body of which a particular point, say the point O, is fixed. So that as one point is fixed, this point cannot have any translational motion. So the rigid body with one point fixed has only 3 degrees of freedom, and all the 3 degrees are related to the orientation of the body in space. Let us consider a body. So if we consider such a body, that it is a body, so and we have a point O fixed, then the body may rotate about any axis passing through this. If we call n cap, this is the instantaneous axis of rotation, so body rotates about this. As the body rotates, the direction of n cap also changes. If we select a frame, S frame, inertial frame, which has the same origin as O, then in S frame, we have omega is equal to I cap omega x plus j cap omega y plus k cap omega z, and the position vector of the ith particle is I cap xi plus j cap yi plus k cap omega z. So if we want to calculate the rotational aspect, the first quantity that we want to calculate is the angular momentum. So the angular momentum L, we start with the basic definition is that summation over I over Li, the individual angular momentum, and this is equal to summation over I Ri cross now this Vi can be written as Ri cross omega cross Ri. So this is written as summation over I mi omega times Ri square minus omega dot Ri times Ri. Since in this case for rotation about a fixed point omega and R both have three components, all the 3 Cartesian components, the expression is a bit complicated, but a bit lengthy, not complicated. I calculate the x component of this, which is I cap. So if we consider this component, here the contribution comes from summation over mi. This is Ri square omega x, and this part is omega x xi plus omega y yi plus omega. So this is minus omega x xi plus omega y yi plus omega z j I, and if we take the x component, this gives us the xi. So for omega x component, this is xi square plus yi square plus ji square. This gets cancelled, and we can write it as summation over mi xi square plus yi square omega x. For omega y, the component comes from xi yi omega y, and this is x. xi zi omega z. If we introduce the moment of inertia, then this is written as ixx omega x plus ixy omega y plus ixz omega z. So we write Lx, we write Lx as ixx omega x, ixy omega y, ixz omega z. Similarly, Ly is written as iyx omega x, iyy omega y plus iyz omega z. Lz is written as ijx omega x, ijy omega y plus izz omega z. This we may look upon the vector L, which is I cap Lx plus j cap Ly plus k cap Lz. Another equivalent way of writing this vector is a column matrix Lx, Ly, Lz. Similarly, this omega can also be written as a column matrix I cap omega x plus j cap omega y plus k cap omega z, which is equivalent to omega x, omega y, omega z. So if we write this expression as Lx, Ly, Lz, then for omega we have omega x, omega y, omega z. To get back this relation, we must introduce a 3 by 3 matrix over here, which is this is Iyx, Iyy, Iyz, Ijx, Ijy, Ijz. So that for Lx, this is Ixx times omega x plus Ixy times omega y plus Ixz times omega z. This is the relation. So this is a matrix form of writing all these three equations. Alternatively, if we can also write it an equivalent notation, we write it as a vector L is equal to, we write it as moment of inertia tensor, and this is an omega. So if we look at it, it is a vector, it is a vector, it is a tensor, it is a column matrix, it is a column matrix, it is a square matrix of order 3. Now, what happens to the calculation of torque? The calculation of torque in this space fixed frame becomes horribly complicated, because we need to differentiate each of these things, and remember that for instantaneous axis of rotation, these components of moment of inertia are not at all constant. They also changes with changing direction. One, and there is an equivalent way of writing this matrix in its component form, which is L alpha is equal to summation over beta I alpha beta omega beta, where the I alpha beta were defined for a given instantaneous axis of rotation mi ri squared delta of alpha beta minus xi alpha xi beta. And for continuous distribution of charge, this becomes rho of r times r squared delta of alpha beta minus x alpha x beta integrated over the entire volume over which the rigid body is distributed. So since the calculation of torque is very complicated in space fixed frame, we skip this part for the time being, and we shall calculate the torque by introducing the principal axis coordinate system. We switch over to the calculation of kinetic energy. So remember this relation which will be used in the calculation of kinetic energy. So the kinetic energy of a rigid body rotating about a fixed point has only the rotational contribution, and we write it as Tr is equal to half summation over I a by Vi square, which we write as mi Vi dot Vi, and for Vi we write omega cross Ri. This is half summation over I mi omega dot Ri times Vi. This can be written as omega dot, and the rest part is half Ri cross mi Vi. So this is the angular momentum L, so this is half omega dot L. If we write L in its component form, means L is equal to, if we write L as I cap Lx plus j cap Ly plus k cap Lz, then kinetic energy operator Tr becomes half Lx omega x plus Ly omega y plus Lz omega z. And if we replace the expression for Lx, recall that L alpha was summation over beta I alpha beta omega beta, that is Lx was Ixx omega x plus Ixy omega y plus Ixz omega z, etc. So if we use this expression becomes half Ixx omega x square plus y omega y square plus Izz omega z square. These are the diagonal contributions, and then twice Ixy omega x omega y plus 2Iyz omega y omega z plus twice Izx omega z omega x. If we, this has come because of the fact that as Lx is equal to an etc. similar expression for Ly and Lz, which has been put over there. So when we multiply this by omega x, the expression is Ixx omega x square. This is, and then Ixy omega x omega y. There will be another term coming from Ny, so which makes it the contribution to, and similarly this term. So when we multiply such three terms, there will be altogether 9 terms. 1, 2, 3, and there are 6, 2 in each of them. So these are the 9 terms. Mm, If we if we consider a space spanned by omega, so in omega space, that is a space spanned by the axis omega x, omega y, omega z, which in this case is the space fixed frame for a given PR. This is an equation of ellipsoid. This we get an ellipsoid called energy ellipsoid. Because for a given value of the kinetic energy, we have a fixed ellipsoid, and the size of the ellipsoid increases, or the volume of the ellipsoid increases with increasing kinetic energy. We may look upon this equation in another angle. We write PR is equal to half omega dot L. But we know that L is, this is half omega dot I dot omega. But in this case, if we write the matrix form, this is a 3 by 3 matrix. This is a 3 by 3 matrix in matrix form. This is a column matrix, so 3 cross 1 matrix, and this one is a scalar, that is 1 by 1 matrix. So for the matrix multiplication to be possible, this should be a matrix, this is a row matrix. So we put a transpose of omit. So this should be transposed to 1. That could be written in a much better form by using Dirac's bracket notation. This is bra omega I tensor kit omega, which is implied that it is a row vector. If we write it explicitly, this is omega x, omega y, omega z. Then we have the I tensor, and then we have a column omega x, omega y, omega z. So if we carry out the calculation, you will land up with the same expression for the kinetic energy. So we see that the rotation of a rigid body about a fixed axis is a bit complicated. However, we can write this in a compact form by introducing double sum as I alpha beta omega alpha omega beta. Now, as I have pointed out that the calculation of torque is very much complicated in body fixed frame. So the entire discussion that we have presented after this, we have used the space fixed frame. Sorry, this is done in space fixed frame, and we remarked that the calculation of torque becomes very complicated in space fixed frame. This is mainly due to the fact that when a body rotates about a fixed point, the direction of the axis of rotation changes continuously, and as a result, the moment of inertia that we have called, this refers to the moment of inertia about an instantaneous axis of rotation. When we perform, and we have written the expression for angular momentum, when we want to get the torque, we have to differentiate it with respect to time, and then not only the components of omega undergo differentiation, but the i's also undergo differentiation, and the resulting things becomes horribly complicated. Alternatively, one introduces the coordinate system is called principal axis coordinate system, PACS. It is a frame fixed with the rigid body at its center Cn, and the ball it rotates with the rigid body, that is, it is rigidly fixed to the body. We may look upon this in another way. This is the if we call the moment of inertia tensor, it is Ixx, Ixy, Ixz, Iyx, Iyy, Iyz, Izx, Izy, and Izz. We consider the eigenvalue problem of this. So we write I times, say, E1 is equal to I1 E1, where E1 is the eigenvector, first eigenvector having eigenvalue I1, and this is and I3 is equal. Now, moment of inertia tensor, this is being a real symmetric tensor, so it is in Hermitian. It is in Hermitian matrix. So these eigenvectors are orthogonal. So Ei, Ej is simply delta Ij. So these are the orthogonal eigenvectors. If this moment of inertia is written in S frame, if we construct, say this is the coordinate system, y, x, z, which defines the S frame, and we consider another frame whose axes are E2, E1, E3, and as the body rotates, this E1, E2, E3, these unit vectors or the direction along these unit vectors, they also changes. So we can consider this frame as the S prime frame, and this is the this S prime frame that we talked about. If we write I in PACS frame is equal to ID, which is simply I1 0 0 0, I2 0 0 0, I3. Recall your concept on matrix diagonalization. This E1 has three components: E11, E21, E31, and we construct a matrix E, which is E11, E21, E31, E11, E12, E13, E21, E22, E23, E31, E32, E33. that is this matrix E. Matrix E is the E1, E2, E3. That is the model matrix that we have introduced in connection with the small oscillation. And if we transform this, if we transform this, then if we transform E transpose I E, then it is the I diagonal, which we have talked about, and the diagonal elements are the eigenvalues of the moment of inertia tensor. So such a coordinate system is called the principal axis coordinate system, in which the moment of inertia tensor is a diagonal one. Now recall what happens to omega and L in such a coordinate system. So in PSCS system, we write omega is equal to E1 omega 1, E2 omega 2, E3 omega 3, and we write L is equal to E1 L1, E2 L2, E3 L3, and we know the relation that L is equal to and ID in this case, and if we rewrite it as L1, L2, L3, this is I1, 0, 0, 0, I2, 0, 0, 0, I3, omega 1, omega 2, omega 3, then we have L1 is equal to, this is omega 1, I1 omega 1, L2 is equal to I2 omega 2, L3 is equal to I3 omega 3. So it is a very simple relation. Li is equal to II omega I. The cross term are not there. And if we write the energy expression, kinetic energy expression, this becomes half I1 omega 1 square, I2 omega 2 square plus I3 omega 3 square. There is no coupling between the angular momentum of belonging to different directions. So this is a very convenient technique of introducing principal axis coordinate system. And since the moment of inertia tensor is a non-singular tensor, we can always find a coordinate system, PSCS coordinate system, for each and every rigid body. As for example, if we have a rigid body which is confined in a plane, that is the rigid body in the form of lamina, then the two principal axes will lie in the plane of the lamina, and the third one is perpendicular to the plane. As for example, if we consider a uniform lamina in the form of a rectangle, then the two principal axes will be directed along the diagonal of the lamina, and the third one is perpendicular to the plane of the lamina and passing through the point of intersection of the diagonals. We shall calculate this principal coordinates, or the moment of inertia, principal components of moment of inertia in a separate lecture. In the next class, we shall extend our discussion to the Euler's equation of motion, Euler's dynamical equation of motion, in principal axis coordinate system.